Now we are ready to prove the main theorem of this lecture. That is, if each function fi for I runs from 1 to m is continuous at a point x bar in the domain of the function f, then we have this nice subdifferential formula. In the previous proposition, we already showed that the opposite inclusion here is satisfied without assuming the continuity of fi. Now, under the assumption given here, we are going to show that this inclusion is satisfied. Okay, so in order to continue, we fix any element v in the set on the left hand side and show that v belongs to the set on the right hand side. Okay, fix any v in the subdifferential of the function f at x bar. Then, by the geometric characterization of subdifferential, we have that v minus 1 belongs to the normal cone to the epigraph of the function at x bar f of x bar. Now, because f is the max of fi for I from 1 to m, we have that the epigraph of f is equal to the intersection of the epigraph of fi, where I runs from 1 to m. The proof of this is very easy. We only need to apply the definition of the epigraph. Okay, so if x gamma belongs to the epigraph of f, then we see that this is equivalent to gamma is greater than or equal to f of x, and this is true if and only if gamma is greater than or equal to fi of x for all I from 1 to m. And from here, we see that x gamma belongs to the epigraph of fi for all I from 1 to m. And therefore, this equality holds. Okay. Now, we are going to apply the normal cone intersection rule in order to continue the proof. And in order to apply the normal cone intersection rule, we need a condition. We need that the intersection of the relative interior of APFI, where I runs from 1 to m, is non-empty. And actually, under the assumption made, we're going to show that this condition is satisfied, and then use the normal cone intersection rule. Okay, so we also have the following. The relative interior of fi, of the epigraph of fi, is equal to the set of all x gamma in Rn times R, such that x is in the relative interior of the domain of the function fi, and gamma is strictly greater than fi of x. We used this repeatedly in previous lectures. Now, because each function fi is continuous at x bar, we see that the interior of the domain of each function fi is non-empty. So by the previous lemma, the relative interior of the domain is the same as the domain of the function. So this is the set of all x gamma in Rn times R, such that x is in the interior of the domain of the function fi, and gamma is strictly greater than fi of x. Okay? Because each fi is continuous at x bar, we see that x bar belongs to the interior of the domain of fi for all I from 1 to m. This again follows from the previous lemma. So by this representation of the relative interior of the domain of each function fi, we can easily see that this element x bar, f of x bar plus 1. Okay, remember that f of x bar is the max of fi of x bar for all I from 1 to m. Okay, so this element satisfies this condition. First of all, x bar here is in the interior of the domain of each function fi, and here gamma is equal to f of x bar plus 1, so it's strictly greater than f of x bar, and f of x bar is greater than or equal to fi of x bar for every I, so gamma here is strictly greater than fi of x bar. So from here we can easily see that this element belongs to the intersection of the relative interior of the epigraph of fi, where I runs from 1 to m. Let us now apply the normal cone intersection rule in order to continue the proof. Now, because v minus 1 is in the normal cone to the epigraph of the function f at x bar, f of x bar, and the epigraph of the function is the intersection of the epigraph of fi, where I runs from 1 to m. So by the normal cone intersection rule, this normal cone can be represented as the sum where I runs from 1 to m of the normal cone to the epigraph of fi at the point x bar, f of x bar. Okay? Now, if we let alpha be f of x bar, then from the definition of the active index set, we see that f of x bar is equal to fi of x bar if I belongs to this active index set. But if I is not in this set, then fi x bar is strictly less than f of x bar. So from here, you can see that this element x bar alpha is in the interior of the epigraph of fi. So in this situation, the normal cone at such a point reduces to 0. Okay, so now in this sum, we can eliminate those elements and have the following. Then v minus 1 belongs to the sum where I runs in I of x bar of the normal cone to the epigraph of the function fi at x bar f of x bar. Okay, so from this representation, then v minus 1 can be written as the sum where I runs in I of x bar of vi minus lambda I, where vi minus lambda I belongs to the normal cone to the epigraph of the function fi at x bar fi of x bar. And over here, remember that because I runs in I of x bar, fi of x bar is the same as f of x bar. Okay. By the previous lemma, lambda I is greater than or equal to 0, and vi belongs to lambda I times subdifferential of fi at x bar. Okay. Now, if we look at this representation, we see the following. V is the sum of vi, where I runs in I of x bar, okay, from this formula, the first part of the formula. And this element belongs to the sum of lambda I. Here it is the subdifferential of fi x bar, where I runs from 1, where I is in I of x bar. And again, from this formula, we also see that the sum of lambda I, where I runs in I of x bar, is equal to 1. Okay. So now we can pick a wi in the subdifferential of fi of x bar such that v can be represented as the sum of lambda I, wi, where I runs in the active index set I of x bar, and remember that the sum of lambda I over here, where I runs in I of x bar, is equal to 1. Okay. Now, because each wi is in this subdifferential, it is in the union of the subdifferential of fi of x bar, where I runs in I of x bar. Okay. So now v can be represented as a convex combination of elements in this union. Therefore, v belongs to the convex Hall of this union. So we have proved that whenever we take any element v in this subdifferential, v belongs to this convex Hall. Therefore, we have this inclusion and complete proof.